Hello, third graders. Today we're going to take a look at lesson 19 from module 7. And today we're going to kind of revisit how to design rectangles with a shared area. And then we are going to kind of introduce a new skill, which is creating line plots. So let's take a look at number 1 and kind of refresh our memories back to producing rectangles that all have a common area. So it says use unit square tiles to make rectangles for each given number of unit squares. Complete the charts to show how many rectangles you can make for each given number of unit squares. The first one is done for you. You might not use all the spaces in each chart. Okay, so since we are in distance learning mode, I actually don't have square tiles or cubes with me, and I'm not actually going to go ahead and make any. You could, but I don't really feel like it's going to be necessary since we completed this module already and you guys were really successful with it. So we're just going to review the strategy that we used to create figures with a shared area. So just as a reminder, where it says use unit square tiles, right? Anytime you see that word tile, that's telling you they're having you take a look at area. So on this one, it's telling us that we want to create areas with 12 square units. And if you look, this is kind of like the T-charts we were making before, right? We were kind of drawing a line, creating a T, putting the area of 12 right here, and then kind of systematically figuring out what times what equals 12. Because remember, area equals length times width, right? They have it flipped as width times length, but basically same thing, right? Commutative property tells us that. So here you can see they started off with 1. Is there anything times 1 that equals an area of 12? 1 times 12 does. Is there anything that creates an area of 12 with 2? 2 times 6 does. Is there anything that creates an area with a side length of 3? 3 times 4 equals 12. And then if I were to continue on and to put 4 here, right, I would hit the flip. That's what we call the flip. And when we hit that, it means we're done. So they did this first one for us, which means that if we're trying to create rectangles with an area of 12, there are 3 possible configurations we can do. We can do a 1 by 12, a 2 by 6, or a 3 by 4. So let's go down to an area of 3 where it says number of square unit squares, right? Unit squares are the same thing as tiling a space. So I have to think. We always know there's going to be something times 1 because 1 times that number always gets us that number. So 1 times 13 gets us an area of 13. So then I'm just going to kind of mentally go through my checklist. Is there anything times 2 that equals 13? No. Is there anything times 3 that equals 13? Nope. Times 4? Nope. In fact, hold on here. I'm trying to fix something. 13 is what we call a prime number. So this is not vocabulary meant to be embedded in here, but we're going to go ahead and revisit it because you know I love to do that. So a prime number is a number that can only be divisible by itself or 1. So 13 is actually a prime number. Now let's move on to 14. So an area of 14 square units, if I start with 1, I have a 1 times a 14, right? 2, is there anything times 2 that equals 14? Yeah, 14 is an even number, and the opposite of prime here is going to be a composite number. So it's a composite number. So I can say 2 times 7 equals 14. I would go on to 3. Anything times 3? No. Anything times 4? No. 5? No. 6? No. And then I hit 7. So if I were to put 7 here and the 2 here, I would have hit the flip. I'm done. I made 2 rectangles here. And on this one, I made one rectangle there. Continuing on then, I have 15. And here you can really see, right, where it comes in handy to have those math facts mastered, because you have to really kind of keep working through fact after fact to find that area. So for 15, we all know there's going to be a 1 times 15 for sure. Now, 15 is an odd number, and it looks like it could be prime, like 13. But it's not, because there is something else that can multiply up to 15. It's not a 2 fact, but it is a 3 fact. 3 times 5 equals 15. 6 times anything? No. 7 times anything? No. 8 times anything? No. And I accidentally skipped over the 5, right? I should have done 4 times anything? No. 5 times anything? I would have hit the flip, and I wouldn't even have gotten to 8. I don't know if you caught that mistake, but I eventually did. So I made one rectangle that was 1 by 15, a second rectangle that could be 3 by 5. And so I've made 2 possible rectangles. So continuing on, now I have 16. So a good strategy to do also is to look at that number and think, is it even or odd? It's even. So that helps us know there's for sure going to be more than one rectangle, because even numbers can be divisible by 2. So always start with the 1. Don't let that obvious one become so obvious that you forget it. 1 times 16 equals 16. I know it's an even number, so I just have to think of my 2 fact. 2 times 8 equals 16. 3 times anything? No. 4 times anything? Yes. 4 times 4 equals 16. And once we hit a double like this, we have the flip, because we're pretty much done. So if you hit a double or if you hit a flip, you know your stopping point has arrived. So we made 3 rectangles here. Next one is 17. So 17 is an odd number. And looking at 17, it looks a little suspicious, right? Like, is it a prime? Is it a composite? I have to say, I don't know any multiplication facts other than 1 times 17 that equals 17. So 17 is another example of a prime number. Prime numbers are only going to produce 1 possible rectangle. And I'm going to get back to that in 1 second. Now, I said 1 possible rectangle, and you might be thinking, hey, but Mrs. Saka, you could do a 17 by 1. Remember, a 17 by 1 still has the same side lengths as a 1 by 17. It's just flipped. So you can't count that as a different rectangle. Okay, continuing on, we have an area of 18. 18 is an even number because 8 is an even number. So I can start off with a 1 by 18. I know it's going to have a fact of a 2, right? So this is becoming what we can see as clearly a composite example of a number. 2 times 9 equals 18. Is there anything times 3? There is. 3 times 6. Anything times 4? No. 5? No. 6 would be the flip. I'm done. This one has 3. All right, so now we get to move on to something new, which is line plots. Now, line plots are pretty cool. They kind of work like a number line, except they're also a way of visually showing data. So we have a number line here that starts at 12 and ends at 18. We can see we're working in wholes, so don't panic. We're not going back to fractions on a number line. So I just have to think, okay, I have to fill this in, right? So I have 13. I would have, my spacing probably could be a little bit farther apart here. So I've got 13, 14, 15, 16, 17, 18. All right, not perfect, but not awful. So now what it's asking us to do is to create a line plot. So like I said, line plots focus in on data. And it says, use the data that you collected in problem 1. So they're basically asking you to show the number of unit squares used down here. That's the 12, the 13, 14, 15. So these are our areas listed below. And X is going to equal 1 rectangle. So how many different rectangles were produced by each of these areas? So I got to go to 12. And I can see up here at 12, we made 3 rectangles. So remember, my key is telling me X equals 1 rectangle. Always pay attention to that because sometimes they'll mix it up on you. So I have 3 rectangles for 12. Now, when you're creating line plots, again, you want to kind of use a consistent size X and consistent spacing so that you can visually see, kind of like a bar graph, which ones are taller or shorter, and you can use them to actually compare. 13 was prime, right? So that was only 1 rectangle. So again, I'm trying to keep them somewhat level. 14, you have to kind of keep flipping back and forth, had 2. 15 had 2. So when I go to do these, you know, these 2 should be hitting in about the same spot. It's okay if it's not perfect, but again, line plots are a tool to use to compare data points. So 16, area of 16 gave me 3, 17 gave me 1, 18 gave me 3. So I'm just going to say 3, 1, 3. Okay, so I've got 3 here. 1 for 17 because it's a what? Yes, prime. And then 3 for 18 because it's a what? Yes, a composite. All right. It says here, which numbers of unit squares produce 3 rectangles? So now I can quickly look at my data and see, okay, 12 produced 3 rectangles, 16 produced 3 rectangles, and 18. So areas of 12 units squared, 16 units squared, and 18 units squared had 3 rectangles. Okay, and remember, I'm doing units squared because, again, we have just shifted into our area file bank and out of our perimeter file bank, and we are focused on the inside of these rectangles. Number 4 says, why do some numbers of unit squares, such as 13, only produce 1 rectangle? Well, what's the vocabulary I introduced over here? We get to get all fancy with our language. 13 and 17, what did we say about them? Yeah, we said they were prime. So they only make 1 rectangle, or I should say, well, some numbers. Okay, we can keep it a they. They only make 1 rectangle because they are prime. That means they are only, that means, and this is good practice to write this definition down, that means they are only divisible by 1 and themselves. Okay, so that's the definition of a prime number. And that's it. So good luck today. Have some fun doing the line plots. They're kind of a nice way to organize information and are pretty useful. See you next time.